In this paper, we delve into the various methods of perturbation-based attribution, including feature ablation, Shapley value sampling, LIME, and kernel SHAP. Feature ablation is a simple method that substitutes each feature with the corresponding element of the baseline feature vector to estimate its importance. Shapley value sampling assigns scores to input features based on their contribution to the model output, providing an unbiased estimate of Shapley values. LIME, or locally interpretable model explanations, samples points in the neighborhood of the input point and trains an interpretable model based on the local evaluations. Kernel SHAP is a special case of the LIME framework that approximates Shapley values by defining the sampling approach, interpretable model, and regularization in a specific way. We also explore other gradient-based methods such as deep lift and layer-wise relevance propagation, LRP. These methods require a backward pass of the model on the original inputs but customize the backward propagation of specific functions. They provide alternative approaches to gradient-based attribution by modifying the default gradient functions. We propose new functionalities in Captum version 0.7 to apply attribution methods within Captum for analyzing the behaviors of language models, LLMs. Users can choose interested tokens or segments from the input prompt as features and use attribution methods to quantify their impacts on the generation targets. In Captum, we introduce simple APIs to experiment with perturbation-based attribution methods. These APIs prioritize ease of use and flexibility, allowing users to customize chosen features, mask features into groups, and define appropriate baselines. Users can define and customize features for attribution in the prompt text. They can choose individual tokens, phrases, or even full sentences as features. This flexibility allows for a more meaningful attribution analysis. Baseline choice is important for computing attribution for text features. Users can define custom baselines corresponding to each input feature, ensuring they fit the context of the original text and remain within the natural data distribution. Feature masking is supported, enabling grouping of highly correlated features together to obtain a combined, single attribution score. Attribution outputs are computed with respect to a target function output. By default, the attribution method returns attributions with respect to the most likely decoded token sequence. However, users can also provide a custom function on the output logit distribution to obtain attribution with respect to an alternate quantity, such as the entropy of the output token distribution. Captum 0.7 provides a simple API to apply gradient-based methods to LLMs. These methods are adapted to handle the non-differentiable nature of embedding lookups in LLMs. Attribution scores can be aggregated across embedding dimensions to obtain per-token attribution scores. Finally, we provide open-source utilities for easily visualizing the attribution outputs from LLMs. These utilities allow users to visualize the attribution results in a heat map format, with the prompt along the top, the target string along the left side, and feature importance scores in each cell. The perturbation-based attribution methods introduced in Captum can be used to gain a better understanding of learned associations in LLMs. By obtaining attributions on features like gender, city, state, and occupation, users can analyze why the model predicted certain outcomes and how each feature correlates with those outcomes. Captum's attribution functionality can also be used to evaluate the effectiveness of few-shot prompts in LLMs. By applying attribution methods to example prompts, users can understand the impact and contributions of these prompts to model predictions, providing insights into the model's robustness and generalization capabilities.